Hello everyone, welcome to the lecture 2 of the course Diffusion in Solids. So today before we take up the mathematical framework in solving the diffusion equations, I thought it's a nice idea to just have a quick revision of some of the mathematical concepts which will prove useful when we solve the diffusion related problems in the coming lectures. So the topics I want to cover are differentiation, some graphs and integration. And this are some of the keywords for this lecture. So many of you might already most of you must have done this, but I think it is still worth to just go through it so that you can brush up your concepts. So the first is about the continuity and the differentiability. So this is the definition of a continuous function, that if f is a real function on a subset of real numbers, and then if a point C, let us say, which is lie in the domain of f, then f is continuous at C if limit x tends to C, f of x is equal to f of C. And a function f is continuous if it is continuous at every point in the domain. So that means if the domain of the function is, let us say, 0 to infinity, and if it is continuous in every single point in this domain, then we call the function as continuous function. Now, sometimes you also have what is known as a piecewise continuous function, which is defined as a function that has a number of breaks in the function and does not go to infinity anywhere in the domain. So, for example, I will show you, this is an example of a continuous function, which is f of x equal to x square for all real numbers. And if you draw the graph of this, which is like a parabola, so this is a continuous function. Whereas, for example, take a look at this function, which is f of x equal to x plus 2 when x is less than or equal to 3, and 2x minus 5 for x greater than 3. So here, if you see at x equal to 3, when we are trying to evaluate the limits, okay, anything less than 3, you will get the answer by this equation, x plus 2. So this is 5, whereas anything slightly greater than 3, you will have to use the equation 2x minus 5, which will give you the limit as 1 for x greater than 3. So that means there is a discontinuity here at x equal to 3. However, if you look at the separate portions, x plus 2, which is a straight line, 2x minus 5, which is also a straight line with a higher slope, both of them then are continuous functions. So this is known as a piecewise continuous function. That means it is splitted into the domains where it is continuous. And derivative, how do you define the derivative of a function? It is equal to f dash f x can be written as limit h tends to 0, f of x plus h minus f of x divided by h. If this limit exists, then the function is differentiable. Okay. What do we mean by limit existing? Means that h tends to 0. So if it tends to 0 from the left hand side or from the right hand side, in both the cases the value should come out to be same. That is what we say, that the limit exists. So if this limit exists, then we say that the function is differentiable. Every differentiable function is continuous. I am not going to give proof here about that, but you can feel free to have a look yourself. Now, the differentiation we will be using a fair bit in our course also, and I think most of you are aware of these rules, that if there are two functions u and v, the u plus or minus v, the differential of this is equal to u dash differential plus v dash. So here the prime u dash refers to the differentiation of u. Similarly, the product rule, that means if there are if a function is a product of 2 u into v, so when we want to take this differentiation, how do we do that? So this is equal to u dash v plus u v dash. That means you differentiate first function keeping the second same, plus you differentiate the second function keeping the first same. and when you want to differentiate u by v, then it is equal to u dash v minus v dash u divided by v square, wherever v is not equal to 0. So, this is also known as the quotient rule. So, let us just also take one example of what is known as a chain rule. So, suppose if you want to evaluate f of x equal to sine of x square, now you assume that t is equal to, let us say, u of x which is x square. So, x square, and v of t is equal to sine t. Okay. So, you see that we are defining a function t here which is equal to u of x which is x square, and then v of t another function which is sine t. So, now if I write dt by dx is equal to, that would be 2x, differentiation of x square is 2 of x. For that matter, differentiation of x to the power n is n into x to the power n minus 1. So, therefore, the differentiation of dt by dx will be 2x, and dv by dt will be cos t. So, differentiation of sine is cos. Then the chain rule says that d of df by dx can be written as dv by dt into dt by dx. Okay. So, what we have done is we have differentiated t with respect to x, and we have differentiated v with respect to t. So, we can write df by dx is equal to dv by dt into dt by dx. So, dv by dt is cos t, and dt by dx is 2x. So, therefore, df by dx becomes 2x cos of x square. So, every time when you do, you do not have to actually go through this procedure. You simply, what you can do is, suppose if you want to differentiate sine of x square. So, differentiation of sine of x square is cos of x square, and because inside you have x square, so the differentiation of x square is 2x. So, you can simply multiply. Okay. So, let us move ahead. For example, if you take this here, so 2 root of cot of x square. If I want to differentiate this, so first 2 remains as it is here, then differentiation of root of any root of cot x square. So, we are focusing first on a root of this function, which is equal to 1 by 2 root of the function. Okay. So, differentiation of for example, root t would be 1 by 2 root t. So, following that, this is root of cot x square in the denominator. Now, inside, now there is a cot function. So, a cot function, the differentiation of cot is cosec square minus cosec square x. So, I put minus cosec square, inside it is x square. So, this remains x square. Now, differentiation of x square is 2x. So, this is how the chain rule works. So, you took first the square root function, which gives you the differential 1 by 2 root of this. Then you differentiated cot function, which is minus cosec square x square. Then you differentiated x square, which is 2x. So, if you rearrange a little bit, this is what the answer is coming. Similarly, if I want to differentiate f of x equal to sine of ax plus b divided by cos cx plus d, if you first apply the product rule, the quotient rule, then in here you take cos square cx plus d, then you first let us say take cos cx plus d, differentiate the numerator, which is numerator's differentiation is this is sine ax plus b. So, this is cos ax plus b, and inside, because it is ax, so the differentiation of ax is simply a. So, that is how you get a cos cx plus d cos ax plus b. And similarly, in the quotient rule there was a minus, but when you differentiate cos, another minus comes, and therefore, it is plus sin ax plus b sin cx plus d, and this time it is multiplied by c. So, you can rearrange a little bit here. So, now if we go ahead, so this is the slide I have put to just show you. Quite often it happens not just for, in fact, this course, even maybe later when you do some other course which involve mathematical functions, it is always good to know how the graph of a function would behave. That's why I have constructed few important graphs here and just gave you so that you are aware. For example, this is simplest, the straight line. Here it is a constant function. This is an absolute value function. So, you see this absolute value function is always positive, because even for minus x the value is actually positive. So, this is like a y equal to mod x function. There is a greatest integer function which has a steps, which occurs in steps. So, here this is a kind of a step function. Then this is the graph for a logarithmic function here, exponential and square root function. Just now we saw reciprocal 1 by x. Then you have a function which is a sinusoidal or a periodic function, a quadratic function, and so on. So, there are different types of graphs that are possible. Couple of applications about of the derivatives, the differentiation which we come across. One important is the construction of the tangent. So, suppose if there is a curve which is like y equal to 2x square. Now, if at any point, let us say 1 comma 2, I draw a straight line which touches only this point on the curve, this line is called a tangent to the curve. And the slope of the tangent is given by, if you differentiate this function, then you get dy by dx is equal to 4x. And at this point, if you put the value x equal to 1, the dy by dx is equal to 8. So, that 8 represents the slope of this tangent, and the equation of the tangent is equal to y is equal to 4x plus 1. So, you will see that tangent construction is an important exercise when we talk about the thermodynamic aspects, and therefore it is important to know that the tangent, the slope of the tangent is represented by the derivative of the function. Okay. So, similarly, if you take one more application of derivatives, is to understand the increasing or decreasing nature of the a particular function or of a particular curve. For example, you can also see that this is a function where at this point, if you draw a tangent, since I told you just now that if you draw at a straight line passing only at one point, the slope of it represents the slope of the tangent. Now, here you can see clearly that it is a horizontal line. That means the slope of the tangent is 0. Wherever the slope of the tangent is 0, that is a point of a local maxima or a local minima. So, you can see here, for example, in this curve, at this position the slope of the tangent is 0, f dash of at C1 is 0. Similarly, f dash at C2 is also equal to 0. So, these points are either minima or maxima. But why we have marked them as a point of maxima here is because you can see that the condition is that f dash of x of is greater than 0 just before C1, and it is less than 0 just after C1. So, when it goes from the f dash x goes from greater than 0 to less than 0, then we say that it is a point of local maxima. If is opposite, that means if it goes from f dash x less than 0 to f dash x greater than 0, we say this is a point of local minima. There is a second derivative test also that is possible, that you can evaluate f dash f double dash at the C1, that is the second derivative. If it is negative at that point, then you have maxima. If it is positive at that point, it is minima. So, this is how the derivatives are useful to understand the points of local maxima, minima. So, generally if you want to evaluate whether a function contains any points of maxima and minima, first you differentiate the function, put a particular value of the point in the function derivative, and then check whether it goes to 0 or not, and so on you can identify. Okay. So, then we move ahead. Okay, so we move ahead to the integration. So basically, methods of integration, few methods let us talk about. So the simplest integral is integral x to the power n dx, which is equal to x to the power n plus 1 divided by n plus 1 plus an integer integral constant. Okay. So here the constant comes because you can imagine that if you differentiate this expression to get the original function, this constant differentiation is 0. So that's why it is important to put this constant as this is called as integration constant. For some specific solutions, if there are initial conditions given, then it is possible to evaluate the constant also. But that is done for the definite integrals, where definite integrals we will see later, actually they have a specific value. Sometimes you may be given the cases where you can determine the constants also. So if you apply this for n equal to actually 0, then integral of 1 dx is x plus c. So remember, this is the formula applicable for all n's, but not for when n equal to minus 1. So for when n is equal to minus 1, actually then it becomes 1 by x dx, and the integral of 1 by x is actually log of x plus c. So here some integrals of e power x dx is e power x plus c. Integral of a power x is equal to a power x divided by log a plus c. Similarly, integral of sine is minus cos, and integral of my cos is sine. Okay. So these are the tables available for you in many of the references you can take. So let me show you a couple of examples of how do we solve the integrals. So the first method is known as the method of substitution. For example, if you have to evaluate the integral of this product sine cube x into cos square x dx, then we realize that sine and cos are differential of each other. So in this case, because the sine has a higher power here, so what I write is as sine square x into sine x, and then cos square x is already there. Then sine square x, I can write it as 1 minus cos square x into cos square x into sin x dx. So now if I substitute cos x is equal to t, then the differentiation of that minus sin x dx becomes dt. So now I can replace this here. So it becomes minus of 1 minus t square into t square dt. I simply just open the brackets. It becomes t to the power 4 minus t square into dt, and this becomes t to the power 5 by 5 minus t cube by 3 plus c. And then you can substitute back the value of t, which is cos x. So it becomes cos 5x by 5 minus cos cube x by 3 plus c. Sometimes for solving integrals of more complex functions, then you may have to do what is known as partial fractions. I am just giving you a couple of examples. For instance, if you have a function like px square plus qx plus r divided by x minus a into x minus b into x minus c, if you want to evaluate integral of this function, it can be very complicated, or there is no easy way to do it. Then what you do is you split this function into partial fractions. So you can write it as a by x minus a plus b minus b divided by x minus b plus c divided by x minus c. Then you cross multiply and compare the like coefficients of x, and you will be able to determine a, b and c. Similarly, if denominator has x minus a into x square plus bx plus c, then it can be written as a by x minus a plus bx plus c divided by x square plus bx plus c. A simple example, suppose you have 1 over x plus 1 into x plus 2, you can write it as a by x plus 1 plus b by x plus 2, and here if I multiply here, it becomes 1 is equal to a into x plus 2 plus b into x plus 1. you separate as different powers of x, that means x into a plus b plus 2a plus b. Now, if you compare the coefficient of like powers of x, we know a plus b here, there is no x on the left hand side. So, a plus b is equal to 0 or a is equal to minus b, and 2a plus b, which are the constant terms, is equal to 1. So, you will get a is equal to 1, b is equal to minus 1. And therefore, now the integral can be splitted as integral 1 by x plus 1 minus 1 by x plus 2. We can separate these integrals into 2, and the integral of 1 by x we saw a few minutes back, that it is equal to log of x plus 1 minus log of x plus 2. Just remember that log of x plus 1 minus log of x plus 2 can also be written as log of x plus 1 divided by log of x plus 2. Then another important method of solving integrals is known as integration by parts, where if your integral is a product of two functions, f of x into g of x, this formula says that you can separate this integral as, first write f of x, one of the function, integrate g of x dx, minus integral of differentiate f of x, f dash of x, and then integrate, multiply with the integral of g of x dx, and entire the complete thing with respect to dx again. I will show you this by an example. Let us say you have e power x into sin x. Now, I is equal to integral e power x sin x dx. Then I write I is equal to e power x, integral of sin x is minus cos x. So, this is written like this, minus differentiation of ex, which is ex itself, e power x itself, multiplied by the integral g of x dx, which is minus cos x dx here. Now, this minus minus will come out. So, it becomes plus here, integral e power x cos x dx. Now, how do we solve this? We have to again apply the by parts here. So, you will see that the first term remains like this, e minus e power x cos x. Now, here when you again want to apply by parts, so e power x, integral of cos x is sin x. So, this is into sin x, minus integral of differentiation of e power x is e power x, and differentiation of cos x is minus sin x. So, here this now becomes, you will see that e power x sin x dx is nothing but your original integral I. So, this you can take this side, and 2i is equal to e power x sin x minus cos x, and therefore, I becomes e power x by 2 sin x minus cos x, and at the last step I have also added the constant because it is an indefinite integral. So, an activity question for you, can you evaluate integral of log x dx using the integration by parts? So, then so far what we saw, that the limits, there were no limits on the integral, that means the integrals were indefinite integral. Now, many times you come across situations where you evaluate definite integrals. So, for example, if you write integral f of x dx from a to b, that means whatever the values you get after or whatever the function you get after evaluating this integral, you put the limit f b here and then a and then subtract the 2. So, we will see how to do that in short while. So, if you have an integral a to b f of x dx, you can simply change the variable as long as, so you can put x as t, instead of t you can write u, and the limits remains the same. If you change the limits here from a to b, you take b to a, then you have the minus sign will come. Similarly, you can split the limits into several parts. For example, I can write integral f of x dx a to b as integral f of x dx a to c plus integral f of x dx c to b. Similarly, integral of a to b f of x dx can also be written as a to b integral f of a plus b minus x dx. And one property that sometimes we come across is that integral of f of x dx from minus a to a can be written as 2 times integral f of x dx from 0 to a, provided f is an even function. What does even function mean? That if you replace x by minus x, the value of the function remains same. However, if f is odd, that means if f of minus x is minus of f of x, then in that case this integral goes to 0. So, I am not giving the proofs of this property, but you can refer to any standard calculus book and see for yourself. So, for example, let us try to evaluate this integral 0 to pi by 2 sin x to the power 4 divided by sin x to the power 4 plus cos x to the power 4. And how do I evaluate this complicated function? Now, I make use of the properties of definite integral. So, I call I is equal to the given integral as equation 1, and just now we saw the property that f of x is equal to f of a plus b minus x, that integrals remain the same. So, you may see here. So, here a to b f of x dx is equal to f of a to b f of a plus b minus x dx. So, that property we will use here, and we will write I as 0 to pi by 2 sin 4 pi by 2 minus x, and denominator also we replace with pi by 2 minus x. Now, you may recollect from the trigonometry that sin pi by 2 minus x is cos, and cos x, and cos pi by 2 minus x is sin x. So, if I do that, then this becomes I is equal to 0 to pi by 2 cos x to the power 4 divided by cos x to the power 4 plus sin x to the power 4. Now, what I do, I add these two equations 1 and 2. So, left hand side I get 2i, and then 0 to pi by 2 sin 4x plus cos 4x divided by sin 4x plus cos 4x. So, I am only left with the integral dx. Integral of dx is x, and then if you put pi by 2 minus 0, you get pi by 2, and therefore, I is equal to pi by 4. Now, one thing that you will come across is the differential equations. So, how do I solve differential equations? It actually depends upon the type of differential equations that we get. One particular case that we will encounter is called separation of variables. For example, if your dy by dx is equal to minus 4x y square, given y is equal to 1 for x equal to 0. Now, here what I can do is I can see that there are two functions, one is x, another is y square. So, I can separate my equation into the x and y variables. So, I can write dy by y square is equal to minus 4x dx, and this then separately I can integrate both the sides. So, integral of dy by y square is equal to minus 4 integral of x dx. And if I do that, I get in this side minus 1 by y plus c1 is equal to minus 4x square by 2 plus c2. So, I get minus 1 by y is equal to minus 2x square plus c2 minus c1, which is also another constant as c. To evaluate the c, we use this condition, which is x equal to 0. So, if I put x equal to 0, y is equal to 1. That means c is equal to minus 1. So, the particular solution becomes y is equal to 1 by 2x square plus 1. I hope it is clear. And just towards the end of the lecture, I just wanted to show you once again the graph of some logarithmic and the exponential functions. So, this is the graph you see for y is equal to 10 to the power x. Just for the comparison, I have also put the graphs of y equal to x, x square, x cube and x. Similarly, you can see the graph for y equal to e power x. Here it is y equal to log x. This again y equal to log x with different bases are shown here. So, thanks, and then we will start taking the fixed laws of diffusion and how to solve them in the coming lectures. Thank you.